Hi. So I'm Jennifer Jackson from the University of Birmingham in the UK, and today I'm going to be talking about protecting Zephyr against memory safety vulnerabilities with the CHERI hardware architecture. So the first question to address is, how big a problem is memory safety? And if you look at the research, you'll find that around 70% of all software vulnerabilities are caused by these memory safety issues. So this is about accessing memory outside of the bounds of the intention of the program. So this includes vulnerabilities such as things like buffer overflows, null pointer dereferences, and other kind of outer bounds type issues. So how does this relate to Zephyr? So Zephyr is largely based around the C programming language, which is a non-memory safe language. And this inevitably leads to memory safety issues through errors in the code. At least 100 CVEs have been reported in the vulnerability database for Zephyr. And if you look at these vulnerabilities, around 60 to 70% of those are to do with these memory safety type issues. So going back to the question, how big a problem is memory safety, then it is actually quite a big problem that needs to be addressed. So this is where CHERI comes in. So the CHERI technology does solve this memory safety problem. It's based on open technology, and it's important to recognize that it's a hardware-based solution. So it will prevent your memory vulnerability from being exploited, and it does this down in the actual hardware level itself. So CHERI itself stands for Capability Hardware Enhanced RISC Instructions, and this is a architecture extension for RISC-based processors. And this provides fine-grained access control to memory. It was first developed by the University of Cambridge and SRI, and is being developed over a period of around 15 years. More recently, there's been contributions from industry, so particularly ARM, and the development of the CHERI Morello platform. There's also been contributions from universities, including ourselves at Birmingham, and other government departments. The output of this has created a number of different CHERI development platforms supporting CHERI tools and software, and also the formation of the CHERI Alliance, which is a group of organizations and companies trying to push forward the adoption of this CHERI technology. So right now, it's quite an exciting time for CHERI. It's at the beginning of trying to this industry adoption, and it's been backed by a number of different government departments and also big companies such as ARM, Microsoft, and Google. So why should Zephyr support the CHERI architecture? So one of the benefits of CHERI is that it provides memory safety to existing applications, as well as future applications for Zephyr. So for example, you can take your existing Zephyr application and OS code. Before you would compile it with the Zephyr SDK and onto something, say, for example, the RISC-V. But now you can take that existing code and recompile it with the CHERI toolchain and make it run on a CHERI-based RISC-V with the extended hardware. So you have the same software, but now you have protection from your memory vulnerabilities. So there are some modifications that are needed to the Zephyr operating system to support the CHERI architecture. And I'll explain a bit more about what those are in a minute. But first, I'll talk a little bit about what CHERI actually does and how it works. So the main concept to understand is that pointers are extended to something called capabilities down in the actual hardware. So if you look at a non-CHERI system to start with, and if you think of something like a pointer here, pointing to a buffer in memory. And the pointer itself has an address field that contains the start address of that buffer. The danger here is that it is possible to point to memory outside of that buffer region using some kind of offset via mistakes that you've made in the high-level code. In a CHERI-based architecture now, your address field is extended to these extra fields of information. So now you have extra bounds and permissions, and this now becomes called a capability. And this capability creates a protective boundary around the outside of your buffer region so that you're no longer able to point to memory outside of that region. So, for example, this could prevent a buffer overflow type scenario from being exploited. So what modifications are required to Zephyr to support the CHERI architecture? So the first thing is to provide toolchain support. So this includes a CHERI version of the LVM compiler, linker, and binary tools. The second is to provide board support for the CHERI version of QEMU. So at the moment, this includes the CHERI RISC-V, 32-bit and 64-bit. And these processors can be configured to run either in just a normal RISC-V mode or a RISC-V with the extra capabilities. It also needs to provide support for physical CHERI hardware, and there's also a CHERI version of the GDB debugger. There are also code modifications that are required. So although the CHERI toolchain can compile your C code down into CHERI instructions, we still need to add support to the actual architecture assembly. So this includes adding CHERI instructions to the low-level assembly code, and also adding boot code to boot your device either into a normal RISC-V mode or a CHERI-based mode. There are also other requirements. So, for example, alignment and offset requirements. So your capability now, it takes up more space in memory. So it also needs to be aligned in memory as well. And then there's some other things that also need adding. So things like symbols needs to be taken into account in memory allocation. You also need to add CHERI-based testing and the associated scripts. So in terms of where we are in development for CHERI Zephyr, so far we've got a prototype development release, which is currently part of the CHERI Alliance GitHub repository. And at the moment, this supports the latest version of the RISC-V CHERI extension specification, 0.9.5. So at the moment, we only support the 64-bit architecture. And it's currently running a minimal set of examples. So in order to run these examples, you need to configure the toolchain variant to be the LVM CHERI version, and set up the toolchain path and also the QEMU path. The main configuration to run in capability mode is this config CHERI equals Y that we've added. And this is set by default in the board support configuration files. So here's one example of running the hello world. So you can use the west build commands. And this board support here that we've got here, so we've got the QEMU running on the RISC-V 64-bit CHERI version. And then this Z CHERI PureCap extension on the end tells you that this is what we're going to be building for with the actual capabilities. So this is the hello world output from that. We've also got some further development plans, and we hope to put this back into the main Zephyr tree. So as well as CHERI Zephyr, there's also a number of other CHERI projects that are ongoing at the moment. And you can see what these are if you go to the CHERI Alliance website. So this includes things like all the different types of CHERI hardware that are being developed that are available. Also different CHERI operating systems that are currently being developed, including CHERI Linux, CHERI BSD, and various other CHERI real-time operating systems. There's also links to different CHERI software. So this is the compiler that I was talking about. There's also a version of the ARM, which is CHERI supported, called Morello. And then there's various different C libraries that have been ported to CHERI as well. So the last question here is now the right time for Zephyr to support CHERI? Well, CHERI technology is now taking off. It's starting to be adopted in industry to better secure our products. So I would say that the answer to this is yes, it is. And if you'd like more information about the work that we're doing or more information about CHERI in general, then these are the links that you can follow. Thank you.
So very soon we will put vanilla LLVM in the Zephyr SDK. Right now, the major hurdle for you to push this back to Zephyr is that our toolchain doesn't support CHERI. So my question is, you simplify that you have a fork of LLVM with the CHERI patches right now. Are you going to upstream that to LLVM so that then the Zephyr SDK will naturally inherit that?
So the question was whether the CHERI version of the LLVM will be upstreamed to the yeah. So I believe that they are trying to do that. I think the version that they're based on at the moment for the CHERI is 15, LLVM 15, so they'd need to rebase that against the latest version. I'm not involved in the actual toolchain side of things, so I don't know how what their kind of roadmap is on that, but I do expect that they are looking at doing that as well.
What about chemo? Is that upstream in chemo, or is that?
Again, yeah, I'm not involved in that aspect of it either. So, but I'd imagine that they are looking into that as well.
Yeah, one more question. How similar is this to existing hardware-based control for technologies like LCD?
So the question is, how similar is this to existing hardware?
Yeah, I mean existing solutions that exist in other architectures. For example, there's actually something which was contributed just recently in Zephyr that tried to do something similar. It's called CET, which is an indenting, add-on to the CPU.
Right. Okay. I'm not familiar with that. So, yeah.
What's the result of a invalid pointer access in CHERI? Is it a fault or is it?
So the result of an invalid pointer access at the moment is it will give you a hardware exception, and it will just stop the processor. But one of the things that we want to look at is what do we do then? How do we actually recover from that if we can? So that's kind of like future work at the moment.
So how do I actually set boundaries? I mean, the pointer buffer example that you gave early on, that's pretty obvious. But well, if I declare this valid buffer as, let's say, an array, and it has 16 entries, and I end up with an index 17, then it's obvious that I'm out of bounds. But if I write like a device driver, and I personally know that this peripheral I'm writing it for has a 4 kilobyte register space, and I'm just computing addresses for individual reads and writes, then only I know that I'm out of bounds when I get more than 4K offset. So how can I declare boundaries in particular for, well, pointers that are manually assembled, where I'm not declaring array in the source code, which is obvious boundaries, but just, adding something to a pointer.
So when you create your pointer in your code, it should create your bounds at the same time. So it's how you actually create that initially, and then if you increase your so you increase your pointer as you go along. So when you get to the point where you're trying to point to somewhere that's out of bounds, then that's when it will create the exception.
There was a CHERI work that David Chisnell has been doing
threads and talking about which ones can access which ones can access hardware. Do you think that's something that could eventually be mapped to Zephyr, like similar kinds of capabilities? Or is it a little bit too different at the moment?
Well, I'd say at the moment we're still in the kind of like prototype stage, so we still need to support more of the actual kernel itself. I guess once we get into that kind of stable kind of position, then we'll be able to look more in depth of looking at some extra functionality.
Is there any actual hardware like platforms right now that you can get your hands on other than Qubit?
So there's a development platform that a company is currently creating called Codasip. That's mainly based at the moment on an FPGA development board. But I think there's another company as well that are trying to create a proper kind of like PCB platform. And I'm not sure if that's been manufactured yet, but they're in the process of it.
So where the information about the pointer is stored, it's encoded inside the pointer itself, and then you have to reduce the size in memory that the pointer can address, or you store this information somewhere else?
So are you talking about the actual storing of the pointer information? So the extra bounds and permissions information, the extra fields, so they will be stored next to the original kind of address where the pointer would normally have. So you'd have the address, and then you'd have these extra fields of information. There'd just be a sort of a longer memory space that you're taking up. Yeah, so for the 64-bit operating system, instead of having an address that's 64, you'd have another kind of 64 on top of that. So you'd have 128 bits to represent your pointer.
So, question. So with this enabled, like in Zephyr, would this stop developers from worrying about memory, overflows and just ignore them because we have something like that? I mean, what happens to existing bugs?
So when you a lot of these things will be found when you're doing your testing. So when you test, it'll bring up quite a lot of these problems because it will create these hardware exceptions. And then you'll be able to fix them if you want to. Otherwise, it's going to stop your processor from running. So it's something that you still want to look at and fix.
Okay, but I mean, existing issue will still be visible through that, or I mean, I'm trying to understand. Are we just hiding the problem with hardware, or is that going to help fix issues?
Well, it's to block it.
It's hardcore.
Yeah.
Because now you're aware of it.
Yeah, so it's hardcore.
So instead of execution, we will have machine check.
So a lot of these problems should be caught when you're testing rather than actually in the field. But obviously, if you have like a 0-day attack, then it should stop that from being.
But it sounds like your discussion about what to do on a fault is like still an open discussion, because then there could be, like future versions of this where you can have secure firmware that's going to decide things to do to mitigate whatever may have occurred.
Yeah, that's right. Yeah.
Could it be used for unit tests to detect bugs? Because if now we get a hard fault, in every case we are writing beyond the buffer, so you don't always get a hard fault because maybe you're writing to somewhere where it doesn't matter in normal architectures right now. So could it be used to just always run all our tests?
So yeah, I mean, some of them can be caught by just testing. I think there's slightly difference between running stuff on QEMU and running things in the hardware. So from experience, there are certain things that QEMU doesn't show up. But if you test it, on QEMU and on the hardware, then it will definitely bring up the tests, the scenarios.
So right now, if you run with native sim right now, the simulator board on Zephyr, you can enable address sanitizer and it will catch exactly. But it will say, okay, now you're at the The problem is that when you ship, you cannot ship obviously with a simulator. So this essentially gives you that runtime capability of checking one shift. So even if you haven't, the stuff you haven't got in testing, the whole point is to, if something is discovered, then they can no longer execute, right? So
That's right, yeah, yeah.
I've got a question which is slightly related to your other question. Like, will you, or maybe there are already available some compiler intrinsics for CHERI, which let you restrict the capabilities further, as opposed to just letting the compiler decide it for you. Because maybe I have a big buffer and I'm checking it in small buffers, and I want to, when I pass that smaller buffer, restrict the capabilities to the code that will consume that buffer. Or scenarios like this.
So you're asking whether there's already intrinsics in the, is it the compiler that you're asking? So, so you're talking about the CHERI compiler? Or,
Is there like a header I can include, and then there are like specific functions that are CHERI specific that I can call to control the capabilities a bit more manually?
so, oh, right, okay. So there are some header files that you can pull in from the CHERI version of the LVM compiler to do specific kind of CHERI manipulation. But I think the idea is to try to avoid that as much as possible and just build your system and let the compiler create your sort of low-level CHERI instructions from that automatically. It's called pure capability. And what you're talking about is like a hybrid version where you can kind of manipulate them. I mean, it is possible to do that, but I think in general terms, I'd like to move away from that.
Am I right that it's impossible to avoid for IMMO memories to avoid some keywords or not? Or is it possible?
Sorry, can you repeat that?
So to define the pointer to the IO memory, we should define somehow the pointer, and we should define this pointer with some CHERI stuff. So we need some keyword for this pointer. Is it true? Or?
So when you create your pointer, you'd create it in what would that be, like a structure or something like that,
No,
or your memory?
So I talk about story load to from IO, for example. It need be aligned. It need special rules applied, and yes, as I said before, it's too easy to overrun the buffer, but it will be an unknown for compiler or for CHERI because it's a problem with IO, so it's peripheral problem. So we can define just public pointer for the range of the memory. Okay, this memory 4K, for example, and inside of the software, okay, we can't touch the memory outside the buffer, which protected by CHERI itself. But how to define the base pointer to this memory? Is there some special word or some?
Not built-in. Not built-in, you can say this pointer is restricted.
Yes, exactly. It's built-in. So what it will be?
If you look at the patches there,
yes.
Okay.
Okay. It will be mentioned. It will be at least it will be IO MMO dash with double dash prefix. Something like.
I mean, in case of I/O, there's probably anyway, depending on the architecture, an MMU to help you to prevent you from running out of it.
It's depends on implementation IP.
Yeah.
IP can be implemented in a very interesting way.
That is true.
I think there was a CHERI presentation at a previous CDS that went into like a, I mean, this is a fast talk, so there's not a lot of time. We're already past time, but there was a longer presentation where they went into this before. I mean, obviously they've been working on it for 15 years, so it's probably, the call here is to start putting the infrastructure into Zephyr. But I think individually, if you're interested in it, you should probably, go look at it, the details behind the architecture.
Just a quick, is it the University of Birmingham that's doing the Zephyr work?
Yeah, so specifically Birmingham's doing the Zephyr. Yeah. And then all the other kind of operating systems are being done by somebody else, and the tool chains and everything.
Right.
Yeah. So we just focus on that one thing.